Welcome students. Welcome to the lecture series on signals and systems. In this lecture, we are going to study about the classification between periodic and non-periodic signals. Periodic and non-periodic signals. A signal which has a definite pattern and which repeats itself at regular intervals of time is called a periodic signal. It is called as a periodic signal. And a signal which does not repeat at regular intervals of time is called as a non-periodic signal, or sometimes it is also called as a periodic signal. Mathematically, a continuous time signal like x of t is said to be periodic if and only if it satisfies a relation something like x of t is equal to x of t plus t. And this is true for all t, that is, you can take any value for t between minus infinity to plus infinity, where here t denotes time and capital T denotes a constant. It represents a constant representing the period of the wave with which your signal is repeating. And the smallest value of t, the smallest value of capital T is which satisfies this above condition, x of t is equal to x of t plus t, the smallest value of capital T, we call it as the fundamental period. We call it as a fundamental period, or simply said as the period of x of t. A signal is said to be a periodic signal if the above condition is not satisfied, even for one value of t. Okay, even for any particular value of t it is not satisfied, then this particular signal x of t is called as a periodic signal. Sometimes aperiodic signals are also said to be having a period which is equal to infinite, and we could use this kind of strategy in converting this Fourier series into Fourier transforms after a short while. Okay, please try to remind that. Okay, remember that. And the reciprocal of this fundamental period t, which is called as f. Okay, the reciprocal of this fundamental period t is represented with respect to small f, and we call this as the fundamental frequency. We call as a fundamental frequency of x of t. Okay, the fundamental frequency, and the angular frequency is given by, okay, the angular frequency is given by omega is equal to, the angular frequency is given by omega is equal to 2 pi times this fundamental frequency, or this can be represented as 2 pi by capital T. Okay, therefore you can always say that the fundamental period capital T is equal to 2 pi by omega. You can also say in this way. Similarly, you can always consider a discrete time. This particular definition can be applied for discrete time signals also, and a discrete time signal x of n is said to be periodic if it satisfies the condition x of n is equal to x of n plus capital N for all values of small n. Okay, that is, here this n is going to take all integer values from minus infinity to plus infinity. Okay, and is going to take this integer value. If the above condition is not satisfied even for one value of n, then the discrete time signal is also said to be a periodic. And the smallest value of capital N for which this particular condition is satisfied is known as the fundamental period. Okay, capital N or the capital T, that what we have seen above for continuous time signals, they are called as the fundamental periods. The smallest value of this capital T or capital N which satisfies these conditions is known as fundamental periods. And similarly, the angular frequency omega is given by 2 pi by n. Okay, the angular frequency, and therefore the fundamental period can also be represented as 2 pi by omega. Okay, 2 pi by omega. And I would like to now contribute some of those important points related to these periodic signals. The first one is, whenever you talk about sum of two continuous time periodic signals, okay, if you are talking about sum of two or more continuous time periodic signals, okay, this CONT actually says that it is continuous time periodic signals, like let us consider them as x1 of t and x2 of t. Okay, let us consider them as x1 of t and x2 of t with periods of t1 as well as t2. And these particular sum of two continuous time signal periodic signals may be periodic or may not be periodic, and it depends upon the relation between this t1 and t2. Okay, and I would like to say that relation, what is a relation it is going to be, and the relation, the sum of two periodic signals is periodic. The sum of two periodic signals is periodic only if the ratio of their respective periods, that is, the ratio of this t1 by t2 is a rational number. It is a rational number of two integer values, something like two integer values. Let us consider that it might be representing similarly, simply like k by some n, or some where k and n both represent some integer values. If t1 by t2 represents this ratio of two integers, that is representing a rational number, in such case we can consider that sum of two continuous time periodic signals is also going to be periodic. And the fundamental period of that particular signal, that resultant signal, can be also calculated by considering the least common multiple, that is the LCM of T1 and T2. Okay, the fundamental period capital T of that resultant signal can be simply related with, can be found out by taking the least common multiple of T1 and T2. If the ratio of T1 by T2 represents an irrational number, then the signals x1 of t and x2 of t do not have a common period, and x of t cannot be periodic. That means if at all you are representing some relation, something like x of t is equal to x1 of t plus x2 of t, then we say that this particular sum, which is represented by x of t, is periodic only if and only if t1 by t2 represents a rational number. If it is an irrational number, in such a case they are called as aperiodic signals. And the LCM, or the fundamental period of this x of t, can also be found directly by taking the LCM of the least common multiple of the fundamental periods of x1 of t and x2 of t individually. Okay, and similarly, if you consider, this is for continuous time signals, but however, if you consider the sum of two discrete time sinusoidal signals, discrete time periodic sequences, if you are considering the sum of two discrete time periodic sequences, then definitely the resultant sequence is also going to be periodic. It is always periodic. Okay, okay, sum of two discrete time periodic sequences will represent another periodic sequence, is always periodic. Okay, and I would like to show you some of those examples of continuous time periodic and discrete time periodic signals. Let us consider a continuous time sinusoidal signal which is drawn something like this. Okay, this represents a periodic signal because it repeats the signal. This particular signal will be repeated after every t seconds. Therefore, this signal is now considered, this x of t, which is continuous with respect to time, is considered to be a a continuous time periodic signal. Similarly, if at all you consider a discrete time periodic sequence, let us consider if there lies any particular signal, something like this. Okay, please try to consider this. Okay, there are some values which goes out of bound of this axis, but however, it is considered to be 0 there. In this case, these kind of sequences, okay, since they are repeating with respect to time, after every t seconds, okay, after every t seconds, therefore we call such signal to be periodic sequences. Okay, periodic discrete time periodic sequences. Okay, I would like to show you some of those interesting results with respect to these periodic signals uh, by considering them as some problems. Let us first of all find out whether a complex exponential signal like x of t is equal to, so please try to consider this x of t is equal to e power j omega naught t, okay, as a complex exponential signals. And now let us check whether it is periodic with a period of 2 pi by omega naught or not. Okay, so we are now trying to find out whether this complex exponential signal is periodic or not. Okay, let us, it is given that x of t is equal to e power j omega naught t. Therefore, x of t will be periodic only when x of t is equal to x of t plus capital T. Therefore, what I am trying to do is, now I substitute these values of x of t here, where we'll be getting it as e power j omega naught t is equal to e power j omega naught of t plus t. I have just substituted t with t here, t plus t in this particular sequence equation. Therefore, you could see here this can be simply written as e power j omega naught t is equal to e power j omega naught t into e power j omega naught capital T. This can be resulted from the law of indices, and therefore you could see that you can simply write this equation as e power j omega naught capital T is equal to 1. Okay, and this is valid only when you can write that omega naught capital T is equal to some multiple of some integer multiple of 2 pi. Okay, it represents 1. This exponential value will be 1 only if your omega naught t value is equal to integer multiple of 2 pi. Either it might be minus or plus. In such case only this will be equal to 1. However, for n is equal to 0 also, that is this satisfies. But here, since we require some minimum value for this representations, it generally doesn't consider that n is equal to 0. Therefore, now I can write a relation between for t as capital T, which we call as a fundamental period, and that fundamental period can be represented as 2 pi times n by omega naught. Okay, where omega naught represents the fundamental, the angular frequency here, omega naught, and capital T represents the fundamental period, and represents the time. And thus, the fundamental period, that is the smallest value of capital T, smallest value of capital T of x of t is given by t is equal to, let us consider a positive value for n. Therefore, the smallest value of capital T which satisfies the fundamental period relation is given by t is equal to 2 pi by omega naught. This is how you can show that a complex exponential signal is periodic, and it is periodic with a period of capital T is equal to 2 pi by omega naught. Similarly, now let us check out another problem where I would like to check whether is continuous time signal like x of t is equal to sine of omega naught t plus theta. Okay, this is the definition of a sinusoidal signal. Mathematically, the sinusoidal signals are represented with respect to this. Okay, where the amplitude of this sinusoidal signal is 1 here, and omega naught represents the angular frequency, t represents the time, and theta represents the phase of this particular signal. And now I am interested in verifying whether this continuous time signal x of t is equal to sine omega naught t plus theta is periodic or not. And if at all if it is periodic, let us also find out its fundamental period. Therefore, since it is given that x of t is equal to sine omega naught t plus theta, in order to verify whether it is periodic or not, I need to just check that relation x of t is equal to x of t plus capital T. Now, x of t is given as sine of omega naught t plus theta, and also I substitute t plus t in the place of t. Therefore, this results in omega naught of t plus capital T plus theta. Okay, so and this can be simply written as sine of omega naught t plus omega naught capital T plus theta. Okay, therefore this omega naught, this particular equation will be valid or equal only when this omega naught t, capital omega naught t, is equal to either 0. But however, if at all we consider omega naught t is equal to 0, this fundamental period becomes 0. Therefore, since we need to consider a smallest positive integer value for capital T, therefore I make that omega naught t equal to, this equation will be valid for all values of 2 pi, for all integer values of 2 pi. But since we need to consider, okay, therefore from this relation you can write that capital T is equal to 2 pi times n by omega naught. Therefore, whenever capital T is equal to 2 pi by n by omega naught, this x of t is equal to sine omega naught t plus theta is a periodic signal with a period of 2 pi n by omega naught. However, since we need to consider for the smallest possible integer values, okay, smallest possible positive integer values for t, therefore t is now considered to be equal to 2 pi by omega naught for n is equal to 1. Okay, therefore this shows that sinusoidal signal x of t is equal to sine omega naught t plus theta is periodic with a fundamental period of capital T is equal to 2 pi by omega naught t, 2 pi by omega naught.